In the previous video, we talked about what causes bonds to form, why chemicals form bonds, and the types of bonds they form. Today, we're going to talk about the characteristics of the compounds that are formed by those bonds. So let's review a little bit that elements get a stable octet by either transferring electrons, which forms an ionic bond. They become ions, and then those ions are bound together, or they can share electrons. And when they share electrons, they are being covalent. So you have ionic bonds and you have covalent bonds. Well, that leads us to compounds formed by ionic bonds are called ionic compounds. And because of the nature of this ionic bond, ionic compounds share certain characteristics. So there are certain characteristics that all ionic bonds have in common. That's what we're going to talk about with the ionic bonds. We'll do that with the covalent bonds in a few minutes. So these common characteristics are because of the way that ionic bond works. So the interactions between cations and anions, that positive cation and the negative anion being attracted to each other, is what forms ionic compounds. And it causes them to create what's called a crystal lattice. Okay, it's the structure, the arrangement of repeating pattern of the elements within the compound. So you've got your positive and your negative. You've got a repeating pattern of your positive and negative ions as they arrange themselves so that the positive ions are all surrounded by by negatives, and the negative ions are all surrounded by positive ions. So there's an example here of a crystal lattice. This is actually an example of sodium chloride. So you've got the chlorine atoms are all negative and the sodium atoms are positive, and you'll see how they repeat themselves and they create this nice little pattern. This is actually what causes and gives the crystal shape, and why different compounds, the crystals have different shapes. Like sodium chloride, the crystals are all nice little perfect cubes, and other compounds form nice little hexagons or rhombuses based off of the structure of how these positive and negative ions arrange themselves. And that's what we call a crystal lattice. The crystal structure of the solid is how the atoms are arranged. Ionic compounds all form a repeating pattern based off the positive and the negative ions. So ionic compounds don't really exist as single particles. So covalent compounds, you have single particles. Ionic compounds, you don't really have single particles. What you have is that smallest possible ratio of positive to negative ions in the compound. And we call that a formula unit. So, for example, back to the sodium chloride, you have the crystal. It's a 1-to-1 ratio. There's one sodium for each chlorine. So the 1-to-1 ratio shows us that the smallest formula unit, the smallest part of this crystal, is one chlorine with one sodium. And we call that a formula unit. So you've got the smallest ratio of your positive and negative ions are the formula unit of the ionic compound. Now, the electrostatic attraction, that positive-negative attraction of a cation and an anion, is very, very strong. Electrostatic force is one of the stronger forces. It's a really strong force, and it holds those two really closely together. Because of this, ionic compounds tend to be hard, brittle solids. They hold on to each other. They stay close together. In order to get them to melt, you have to get them moving really, really fast to get those particles to come apart. They do not melt very easily. They have very high melting points, which also means they have very high boiling points. So in order to get them to melt or boil, it takes an immense amount of energy because that electrostatic attraction between the positive and negative is incredibly strong. And if you look at that crystal structure, you also notice that you've got that positive sodium, there's a negative all the way around it. In the negative chlorine, there's positive sodiums all the way around it. And so that interaction between each individual formula unit is also very strong, which makes the overall crystal a hard, brittle solid. However, the attractions between these ions can be separated by other charged particles. Because it's, again, the positive negative attraction. So if you bring in more positive and negative attractions, you can pull it apart. So we can pull it apart by those polar molecules. And we talked about polar bonds a little while ago, or in the previous video. And in a little bit, I'll explain what polar molecules mean. But Water is a polar molecule. And so when we put ionic compounds in water, they dissolve quite easily, most of them. So they dissolve in polar compounds like water. Other polar compounds also they will dissolve in, because that positive negative interaction between the polar molecule and the uh, ions of the crystal will cause the crystal to get pulled apart. All right, we call that a process of them being pulled apart is called dissociation. So when you put a ionic compound in water and you stir it around, you mix it up, the water molecules will actually surround, attract, and pull the negative and the positive ions apart and dissociate. They are associated, so it causes them to dissociate, come apart. All right, and so this is kind of what it looks like. When you put salt in water, you end up with the positive sodium are getting surrounded by the water, and this is the oxygen of water, and so it's got a slightly negative side here, and so that negative side pulls on the positive sodium, and then the hydrogens part of the water are positive, and so they pull on the negative, and it pulls them apart, and it causes it to dissociate. That's actually what is happening when an ionic compound dissolves. It's being surrounded, or we call it solvation. It's being solvated in the polar compound. So those free ions that are formed when ionic compounds are dissolved, so the ionic compound pulls them apart, and so you have these positive ions and these negative ions that are floating around in the polar solution. They allow electricity to travel, because you've got ions, which are charged particles, allow the electricity, which is a movement of charged particles, to flow through it. Right? A substance that will conduct electricity when it's dissolved in water is called an electrolyte. And ionic compounds, most of them are capable of becoming electrolytes. And electrolytes are incredibly important in our bodies. That's actually how our nerves and our muscles work. When you are working out and your muscles are working, they get electrical impulses. Well, those electrical impulses are generated in certain parts of your body, and they're sent through your nervous system, they're sent through your muscles through electrolytes. So if you have the wrong balance of electrolytes in your body, then your muscles don't work correctly. This is actually what causes cramps, and why things like sports drinks replenish those electrolytes, because as you sweat, you lose electrolytes, you lose ionic compounds through your sweat, and your body has an imbalance in those electrolytes. So by drinking that sports drink, you're replenishing those so that your muscles will work correctly. That's what those are for. And that's why it says replenish your electrolytes. That's what it's talking about, because all of the bioelectrical systems in your body work off of electrolytes. And if we don't have the right balance of electrolytes, then our bodies don't work correctly. So that's a fun little interesting thing. So here's an picture here of, you've got a non-electrolyte over here, something that does not conduct electricity, and the light bulb's not on. Some things are weak electrolytes, so they'll kind of ionize a little bit when you put them in water, and so it would conduct a little bit of electricity. And then there's some strong electrolytes that will conduct a lot of electricity. In fact, strong electrolytes are what we use in like liquid batteries, like in car batteries. You've got a strong electrolyte in sulfuric acid, and that's what's in the car battery that allows the electricity to be transmitted. Electrochemistry is really fun and very, very complicated. So anyway, compounds formed by covalent bonds. So those ionic bonds, compounds formed by covalent bonds are called covalent compounds. Covalent compounds are also sometimes called molecular compounds, because that smallest particle of a compound is a molecule. So the smallest part of an ionic compound we call a formula unit, because it's just a repeating pattern of a ratio. But with a covalent compound, you have an actual physical thing. You have a molecule, and that's what a molecule is the smallest part of a covalent compound. So you've got these tiny molecules, and that's why they're called a molecular compound. Sometimes you'll hear people just call them molecular compounds instead of covalent compounds. Molecular compounds and covalent compounds are kind of the same. So the covalent bond between an atoms are very, very strong. So that bond, like in water, the bond between the oxygen and the hydrogen is a very strong bond. However, the bond between molecules is not very strong at all, relatively speaking. In some covalent compounds, there's almost no bond between individual molecules. So the bonds within the molecule, the bonds between atoms where they're actually sharing electrons, are really strong. But the bonds between molecules, individual molecules, are fairly weak. Or non-existent. Those weak interactions between molecules are called intermolecular forces or van der Waals forces. Right? But because of these weak intermolecular forces, molecular compounds tend to have relatively low melting and boiling points because the individual molecules don't really stick together very well. So when I say relatively low, melting points like room temperature, I mean, water turns from ice to liquid water at 0 degrees Celsius is where it makes that transition. At room temperature, which is about 20 degrees Celsius, it's fully a liquid. A lot of covalent compounds like carbon dioxide or carbon monoxide, they're gases at room temperature. Whereas most ionic compounds at room temperature are solids, and you have to get them to 8, 9, 1,000 degrees Celsius in order to get them to even begin to melt. Whereas most covalent compounds will melt at a relatively low temperature. Even if that temperature is like 200 or 300 degrees Celsius, compared to an ionic compound, it's a much lower melting point. So covalent compounds tend to have much lower melting and boiling points because of those intermolecular forces not being as strong in a covalent compound as those electrostatic forces are in the ionic compound. So they also tend to be gases or liquids at room temperature because of this. And if it's a solid, it's usually a soft solid, not really a hard crystal. There are some exceptions to that. Obviously, there's exceptions to everything, but these are just general rules of thumb, general characteristics of these types of compounds. Covalent compounds do not generally conduct electricity. Again, some do, but most covalent compounds do not generally conduct electricity. Most all covalent bonds are polar. We talked about that previously, that covalent bonds are polar because they don't share them equally, because one atom is going to have a higher electronegativity than the other. The exception to that is when they're bonds between the same element, then they share equally. So those covalent bonds themselves are polar, but not all covalent molecules are polar. You can have polar bonds and a non-polar molecule. So for example, we see here, this is a diagram of methane. It's carbon with 4 hydrogens. So the bonds here are very, very polar because hydrogen has a fairly low electronegativity, carbon has a higher electronegativity. So it's going to be a polar bond between the carbon and the hydrogen, and a polar bond here, and a polar bond here, and a polar bond here. But because this is a symmetrical molecule, the molecule itself is not polar. There is not a positive side and a negative side. In order to be a polar molecule, you've got to have a slightly positive side to the molecule and a slightly negative side to the molecule. Well, even though this bond is polar, so slightly positive, slightly negative, slightly positive, slightly negative, the molecule as a whole is not polar. It's because it's symmetrical in all directions. Now, a different example would be like this one, ammonia. You have nitrogen and 3 hydrogens. Again, these bonds themselves are incredibly polar, but the molecule is also polar because there's actually a free electrons up here. We'll talk about this more in a few days, but there's a unshared pair of electrons sitting here, which are pushing those down. And so you have a slightly negative side. Notice you can kind of draw a line here and separate the positive hydrogens from the negative nitrogen. So it's slightly polar, slightly negative side over here and a slightly positive side where the hydrogens are. It is a polar molecule. And this one is a non-polar molecule, even though all of the bonds themselves are polar bonds. So you need to make sure you understand that bonds are polar, but that doesn't necessarily mean the compound is polar. So you have to look at the whole molecule. We'll discuss this more when we talk about molecular geometry in a couple of days. So a type of bond that we did not discuss previously, we talked about ionic bonds, we talked about covalent bonds. Type of bond we did not discuss previously is the metallic bond. Okay, It's not necessarily a bond between atoms of different elements, like sodium and chlorine are different elements, they form ionic bonds. Carbon and oxygen are different elements, and they form covalent bond. But you can have a metallic bond. If you have a chunk of, say, gold, all of the atoms in that chunk of gold are gold, and they're bonded together through a metallic bond. Okay? Now, in metals, what makes it a metallic bond, in metals, electrons are delocalized. Those valence electrons are loosely held by their parent atom, and so they're kind of free to move between atoms. Okay, those valence electrons move freely between atoms in the metal's crystal structure, in its arrangement of the atoms. Those electrons are free to move around and move through it, and we call that a sea of electrons, right? Because the valence electrons kind of move around, which is why we also said that metals have variable valences, because they do, and the valence electrons kind of move around a little bit between the atoms. They're kind of free to move. That's what forms this metallic bond, because you have this negative sea of electrons and this positive, slightly positive portion of the positive parts of the atom are kind of making this electrostatic attraction. So it's kind of bringing everything together and holding them together. So this sea of electrons, though, does explain a lot of the physical properties of metals, right? So metals conduct heat and electricity. Why do they conduct heat and electricity? Well, electrons are free to move, which allows an electric current and heat energy to easily move through the metal's crystal. Because they are free to move, and moving electrical charge is what electricity is, those free to move electrons are allowing the electricity to flow through them a whole lot easier. Covalent compounds do not have that ability, and other nonmetals do not have the ability to allow the electrons to move easily from one atom to the next, and so electrical current is impeded. It's stopped. It's not allowed to move very easily. But since the electrons can move easily from one atom to another in a metal, that because of the sea of electrons, they are easily allow electricity to flow through them. So this metallic bonding is what allows metals to be good conductors of heat and electricity. Metals are malleable and ductile. So if you remember, malleable means it can be flattened or pounded into sheets. Ductile means it can be drawn or pulled, stretched into a wire. And so this happens because of this metallic bonding, because individual atoms are bound together, but they're still able to slide past each other. So they're not stuck in a rigid structure like a salt crystal of sodium and chlorine. You've got that crystal structure where they're all kind of stuck rigidly by their electrostatic charge. Well, since the sea of electrons kind of moves around, the atoms in a metal are not stuck rigidly. They're allowed to move and slide past each other. They may be kind of stuck with each other here, but they can move around in their configuration, which allows metals to be dented and bent and stretched, whereas other solids cannot do that because they're stuck rigid. With a ionic crystal, if I have them stuck together and I apply enough force, they just break. It doesn't bend. It doesn't stretch. It just breaks. Okay? So let's review. Ionic compounds are generally hard, brittle solids. They have relatively high melting points, and they dissolve in polar compounds, and they form electrolytes. So all of this is because of that positive-negative interaction between the atoms in an ionic compound. Covalent compounds are generally gases or liquids or soft solids at room temperature. They have relatively low melting and boiling points, and they can be either polar or nonpolar compounds, even if all of the bonds themselves are polar bonds. And they do not generally form electrolytes. Now, it is possible for nonmetals to be electrolytic, but not generally. All right. Metallic bonds, again, are formed by free electrons in the metallic crystal. They give many metals their specific characteristics like malleability, ductility, and electrical conductivity. And those are the reasons for the properties of metals are the metallic bonding. Okay, so we've talked about the characteristics of bonds and the different types of compounds that are formed by the different types of bonds and those characteristics. All right, moving forward, we're going to be discussing the way that we represent these different types of compounds when we draw them out and showing the structures. And we're going to talk about molecular geometry and the shapes of these molecules. So thanks for watching and have a day.